Welcome friends to the next lecture in the series of antenna and wave propagation. In this lecture, we are going to discuss the fundamental parameters associated with antenna, which is continued from the previous lecture. In previous lecture, we discussed about radiation pattern, its type, what is different types of pattern available to us, the basic antenna radiation intensity, the power density, beam area, solid angle, etc. And on that portion we solve some problems. Okay. In this lecture, continuing the fundamental parameters of antenna, we are going to discuss the directivity, the most important parameter, gain, efficiency, aperture, and later on we discuss the phase transmission equation. So, here is the content: directivity, gain, antenna aperture, efficiency, and radio communication link, which is phase transmission equation. So, in this lecture, the student able to understand or gain the concept of directivity, gain, its relation with efficiency, effective height, aperture of antenna, and most importantly the relation between transmit power to the receive power. Receive power means radiated power, P r to the P t ratio, which is phase transmission equation. So, start with directivity. What is directivity? Directivity is nothing but ratio of radiation intensity in a given direction to the averaged over all direction. So, according to the formula, radiation intensity how represented as u theta phi in a given direction, u theta phi, okay, because it is dependent upon theta and phi. But in case of all average over all direction means isotropic case. So, what is the value? U naught. So, please understand this, u theta phi divided by u naught, and what is its value? 4 pi u theta phi upon p radiate. How? Because u naught is nothing but, we have discussed, u naught is nothing but p radiation divided by solid angle available in a sphere, which is 4 pi. Okay. The radiated power per unit solid angle is nothing but radiation intensity. So, using this formula we will get our this formula, which is the important formula, 4 pi u theta phi divided by p radiation. Next, the maximum value of directivity, how it need to be maximize this value, and u max upon p radiation. Now, we can convert into decibel, 10 log 10 and this value. So, we will get this decibel directivity, and now intensity divided by intensity. So, that is why it is dimensionless quantity, where d is directivity, d naught is maximum directivity, u is radiation intensity, power density per unit solid angle, u maximum is maximum radiation intensity, u naught radiation intensity of isotropic, and p radiation is radiated power by an antenna, unit is watt. Now, there is more further formula, generalized formula. The first formula we understand this, 4 pi u max upon p radiation. There is one more formula, is nothing but 4 pi maximum pattern theta m phi m divided by this beam solid angle. This value is nothing but sin theta d theta d phi, or this is, we can say that, average or generalized value f theta phi. Okay. So, this is one more formula, this is the formula, and this formula is from beam area. This formula from pattern, this formula from intensity. So, there are three different formula utilized for directivity of an antenna. Directivity is nothing but 4 pi per unit solid angle, or total solid angle psi a. Okay. So, again see, this is beam solid angle, only the representation I have changed over here f n, because it is p n. Okay. Do not get confused. Now, next is gain. Once we have derived the directivity, the gain is second important terms which need to be carried out or analyzed by RF communication engineer. Gain play a very important role, because it is not the it is not the available one, it is, but it is realized quantity. we need to realize, and that is why it is always lesser than directivity. Gain is always less than directivity, please remember this. Okay. Now, one more thing in directivity, because we are discussing with reference to isotropic source. So, what is the value of directivity? If you remember this formula, the back one, directivity from solid angle 4 pi divided by beam solid angle. Now, can you tell me what is the value of psi a for isotropic source? The total solid angle in isotropic source, the maximum one, it is 4 pi. So, 4 pi to 4 pi divided by this, how much? 1. So, the directivity of a isotropic source is nothing but unity. Always remember this, directivity is 1 for isotropic source, but for non-isotropic source it is always lesser than 4 pi, because there is no such antenna which can equally radiate in all 360 degree. So, it is always less than 4 pi, and hence this for non-isotropic directivity is always greater than 1. So, please remember this, for isotropic case it is equal to 1, and for non-isotropic it is greater than 1. Okay. Coming back to the gain. Okay. Now, gain is nothing but radiation intensity, 4 pi times radiation intensity to the total input power. Input power is represented as P in, radiation intensity as we know that u theta phi, and the formula is 4 pi u theta phi divided by P input. So, this is one formula. There is alternate formula that is governed from next topic, that is efficiency of antenna. It is a ratio of gain to the directivity. So, gain can be defined as efficiency multiplied by directivity. So, there is one more formula, and this is given by this value, where ECD is nothing but conduction, ECD is EC into ED is nothing but conduction efficiency as well as dielectric efficiency. Okay. So, this way we can define gain of an antenna. Or there is one more formula, that gain is nothing but neta into D naught. D naught again for isotropic case, neta is nothing but efficiency which is defined as P output or P radiated divided by P transmitted, or one more thing, P output divided by P input. This is efficiency. The total power PT supplied to the antenna, a part of P naught is radiated out into space. Whatever the total power available, a portion P naught is radiated into free space. Okay. And the remainder power PL, which is P loss, is remained or dissipated as form of heat in the antenna structure itself, and that is losses. We are discussing about conduction losses and dielectric losses. Okay. So, the radiation efficiency neta L is nothing but P output upon PT. P out is the portion of power available as a radiated. So, P radiation is the term, and PT is the total power. Okay. Total power at input side is nothing but P input. So, this is different types of giving the value P output upon P input, or P radiation upon P transmitted, or P total, sorry. Okay. So, the maximum gain is nothing but efficiency multiplied by directivity. So, this is the formula. Now, next topic is antenna aperture. Antenna aperture is nothing but maximum directivity D naught of an antenna is related by effective aperture AE by this formula. D naught is nothing but 4 pi AE upon lambda square. Okay. So, this way we can define this formula 4 pi AE upon lambda square. Now, we have converted into terms of gain, because directivity is related to how much? Gain G naught is nothing but into D naught. Remember the previous formula in this slide? So, you can convert directivity by gain. So, this is the formula. Okay. So, both way we can represent directivity form or gain form, okay. Or we can derive from here in terms of what is effective aperture. It is nothing but cross multiply G naught into lambda upon 4 pi. So, it is always associated with this. If I know if I knew the directivity, then we can easily calculate gain, because efficiency multiplied by directivity is nothing but gain, and once we calculate this, we can easily compute what is effective aperture. Okay. There is one more term is effective height. This is effective aperture and it is effective height H e, and according to definition it is nothing but induced voltage to the available electric field. It is the ratio of induced voltage to the available electric field, okay. Volt per meter. So, it is nothing but unit is meter, voltage ki volt and this is volt per meter. So, volt to volt cancel out and what is available meter. So, this way we can define effective height. Okay. Now, antenna efficiency and aperture efficiency. Remember, we earlier defined as radiation efficiency E total is nothing but E naught is how much radiation efficiency, which is E r into E c d. What is E c d? E c into E d. E c stand for conduction, E d stand for dielectric losses or dielectric efficiency. So, total it is E r into E c d. This is the total efficiency available to antenna. So, this is E r. Reflection, which is governed by mismatch. This is reflection. How it is governed by mismatch? So, this is nothing but you can see that gamma, current, conduction current, dielectric current, okay, conduction and dielectric current, this way we have defined over here. Okay. So, what is happening? This is the antenna part, this is antenna, okay, and this is transmission line T x line. In short form we write transmission line T x line. Okay. So, at this interface, this point of view, if there is a mismatch between impedances of antenna, there is a reflection, power can be go back. Okay. So, this we have defining over here E r, then E c conduction and D for dielectric. Okay. So, this way we define this formula once more. Reflection is nothing but, remember, gamma is nothing but Z input minus Z naught upon Z input plus Z naught. Z input is the input impedance, and what is Z naught? Z naught is characteristic impedance of that conduction wire. Okay. So, Z input Z naught is characteristic impedance. So, this way we can define the reflection coefficient, and voltage standing wave ratio, what it became 1 plus gamma 1 minus gamma. This is the basic formulation and representation of reflection coefficient and to the voltage standing wave ratio. Okay. And this is the formulation 1 minus gamma square into E c d. So, E naught total efficiency, okay, where E r reflection efficiency, E c is the conduction efficiency and E d is dielectric losses efficiency. Okay. This way we define our antenna efficiency. There one more thing, aperture efficiency. What is aperture efficiency? Aperture efficiency is the ratio of AE to the AP. What is AE? Effective aperture. Remember, AE effective aperture, and what is AP? Physical. What is difference between these two? For example, let us consider a dish antenna, parabolic reflector antenna. Remember this type of structure. Okay. Suppose we are using this type of scenario, reflector antenna. What happened? some portion of power coming from this distance antenna which is transmitted from that side and coming forward over here. So, what is effective aperture? Only this portion is utilized rather than complete structure. So, that is physical and that is effective. One more thing we can say that if total portion is utilized, some power or some thing voltage or maybe current is formed leaking over here. So, it is the effective area total rather than physical area. So, this way we can understand physical what is manufactured one. Okay. There is change in effective only, how much portion of manufacture we going to utilize this. So, this is the difference between physical aperture and effective aperture. Physical aperture is always fixed, which is manufactured, okay, and AE may be changed. So, this is the ratio of AE upon AP, and that is why over here AE is always less than AP, and it may possible that A is equal to AP, but not greater than. Physical से ज़्यादा नहीं हो सकता. Okay, A is less than AP, and therefore this quantity, since A is lesser than AP, is always less than unity. So, efficiency or aperture efficiency is always less than unity. Okay. Now, there is aperture antenna. Now, we discuss in case of wire antenna. What happened for wire means dipole antenna we can take. Rather than this parabolic reflector we can take wire antenna. So, what is the value? Now, see the changes. Effective aperture or effective area is must be greater than equal to physical one. Why it is happening? This is simple wire dipole antenna. Okay. Its physical aperture is very less, but effective is very high. Why? Because the radiation it takes out from this form both side and so on. So, total it comprise look like a bigger one from distance place, and that is why its effective is greater than physical one, and that is why its efficiency is greater than unity. Okay. For aperture it is less than unity, for wire kind it is always greater than unity. Okay. So, this way we are going to solve, and now we can formulate this. For aperture case it vary from 0 to 1. See this 0 to 1. Now, total efficiency we discussed. Now, this is antenna efficiency, we already discussed this. So, we skip this topic. Now, the last topic of this lecture series is Friis transmission equation. Why we discuss gain, aperture, directivity earlier? Because in developing radio communication link we require these things. So, let us assume we have two identical antenna, and this is nothing but horn directional antenna, horn antenna. Okay. This is the structure of horn antenna, this side view. Okay. This is the structure of horn antenna. So, this is the transmitter antenna Tx, this is receiver antenna. So, if transmitter is transmitting like this, the receiver must be aligned into this. So, there is line of sight communication for maximum power. Okay. There must be line of communication. If this is inclined like this, the receiver antenna also aligned like this, not like this. So, how it can intercept the radiated power? It must be aligned. Okay. So, this is the line of sight communication LOS. So, what over here? It transmitting at a direction theta t and phi t. This is transmission theta t comma phi t. Same it receiving angle theta r phi r. R for receiving, T for transmitting. Okay. Now, at transmitter antenna site, let us assume the power available is Pt, directivity dt, gain Gt, and efficiency epsilon t. Okay. These are the factors. Same at receiving side, Pr, Gr, Dr, efficiency ECDR, okay, and this is gamma r reflection. Okay. So, this way we can define. So, this is the basic setup and it is separated by a distance how much, capital R. In far field, R can be termed as 2d square upon lambda. When we discuss field region, we discuss about this formulation. So, R it is separated by in very large distance. So, it is far field quantity. So, distance is always 2d square upon lambda. Now, let us develop this equation. So, at a fixed distance r from the transmitting antenna, the power intercepted by receiving antenna having effective aperture AE is nothing but pointing vector multiplied by that area. So, power is nothing but pointing vector capital S into effective aperture AE. This is the formulation. So, over here because it is receiving side, so SR and effective aperture is nothing but AR. R stand for receiving purpose, okay, T for transmission side. So, remember this bifurcation. So, S is nothing but, so further it can be related PT because power is transmitted from source side, PT divided by 4 pi r square into gain of transmitter antenna into, but it is received by receiving antenna having efficiency aperture effective aperture AR. So, this is the formulation. Now, SR is the received power density, see power density we are talking about, GT is the peak gain of transmitter antenna, okay, and R is the separation distance between transmitter and receiver antenna. Now, this power again same diagram PT, PR, R is the distance, okay, is given by this. Next, moving to next slide. Now, if the radiation efficiency of receiving antenna is this value neta, if radiation efficiency of receiving antenna is neta r, then the power received at the receiving antenna output terminal is how much? The power incident at that angle multiplied by this efficiency, simple. Now, what is the value of power? See this power PT upon 4 pi r square, remember this formula, this from there PT upon 4 pi GT AR multiply by efficiency neta r, just we multiply with efficiency and thus we give rise to this equation PR, okay. So, PT upon 4 pi r square GT neta efficiency at receiver side into AR. Now, further we can rewrite this PR into PT ratio because PR is available over here and PT is available over here. So, Price transmission equation nothing but it give relation between PR upon PT, transmit power and receive power, radiated power, okay. So, PR upon PT. So, what is the value PR upon PT? Again simply we are using the concept of this value, gain is nothing but 4 pi AE upon lambda square, remember this aperture 4 pi, sorry, this is gain is equal to 4 pi AE upon lambda square, okay. So, we can convert either into gain formula or in terms of effective aperture by cross multiplying this value. So, over here which is given in terms of gain and second terms it is given in form of effective aperture. So, this way we can clarify in two different perspective in terms of gain, in terms of effective aperture. One more thing we can relate in form of directivity, gain is nothing but efficiency multiplied by directivity, remember this formula. So, this way we can convert gain into directivity or even directivity to this value effective aperture. So, this is a conversion between different formula because sometime different aspects or different types of numerical is asked where effective aperture is need to be calculated. So, you need to calculate directivity again first, or effective aperture is given you need to find out PR upon PT ratio. So, you need to directly utilize this formula, okay. So, depending upon the question type you can realize your formula according your usage, okay. So, PR upon PT is nothing but lambda upon 4 pi r ka whole square, lambda upon 4 pi r ka whole square, okay, into GT GR, okay. How? Because AR is converted into this formula, AR is nothing but GR into lambda square upon 4 pi, from this formula, when you put over here, what we get? Lambda square term, 4 pi r square, and this is 4 pi. So, 4 pi square. So, total lambda upon 4 pi r ka whole square. This way we can rewrite over here. Okay. Now, this is g t, and this value we have converted into this form. So, g r. Okay. So, this way we can rewrite. Next, we have converted g into effective aperture. So, again same formula. For transmitter side it is AET or AT, for receiver antenna it is AR. So, from here we can rewrite this formula again. One more thing, you can formalize this formula in terms of directivity. Okay. So, here neta into this value is nothing but directivity. So, this way we can find out our relation of phase transmission equation. So, if now since we are giving the spatial direction, so theta t phi t, remember the first figure, and receiver side theta r phi r. So, this is the formula, always remember this formula. This is very important relation of P r upon P t is nothing but lambda upon 4 pi r ka whole square into gain of transmitter antenna into gain of receiver antenna. Most of the cases, if identical antenna are used as a transmitter and receiver purpose, so gain of transmitter antenna is equal to gain of receiving antenna. If isotropic or identical antennas were used for transmission and reception, then g t theta t phi t is equal to g r theta r phi r. Okay. Please remember this. If identical antenna, both side it is used same antenna, then the value of gain is also same. Okay. So, where theta t and phi t is the direction of receiving antenna and transmitting antenna coordinate, okay, vice versa. So, this is the complete phase transmission equation, okay, and this is very important relation between the received power to the transmitted power, and most importantly it is inversely proportional to the square of the distance. See, it is inversely proportional to 1 upon r square, and what it represent? As the distance goes on, the relation is become poorer. Okay. So, and more thing, it is directly proportional to lambda. Lambda is nothing but wavelength, okay, and wavelength lambda is equal to how much? C by f. If frequency is increasing, lambda is decreasing. So, higher the frequency, the ratio is again smaller, and again this term is g t and g r gain, which is directly proportional to this ratio. Okay. So, this way we can analyze our phase transmission equation. You can further analyze in form of directivity, okay, or we can further analyze in terms of effective aperture. See the formula, previous cases we can easily convert, because gain or directivity is nothing but 4 pi A e upon lambda square. From that formula we can rewritten this formalization into terms of AE and also in terms of directivity. So, this is about the phase transmission equation. Thank you.